This is something we are not really pushing and not really hiding, but you're probably one of the few guys to see our closest plans again. I had touched it a little bit when I was talking about SPDK and then NVMe as a Fabrics protocol about the capacity nodes, and also talked that StarWind is not, with the storage, we are not going, I mean, we're trying not to go beyond the 2 or maximum 3 controller nodes, adding the raw capacity with the JBoards. And it's okay right now because we do not serve the customers. I mean, we have some customers who have petabytes of storage, but the workloads they have, it's, let's say, not all hot data. But we're looking to get into 2 new areas. And one of them is doing the proper scale-out storage. So on this picture, you see that on the top, there's a bunch of guys who are acting as storage consumers. These are VMware, Hyper-V, Linux, and whatever you can make talk, iSCSI or SSD, maybe a talk. Then we get StarWind controller nodes. And they do have dynamic memory caching, they have flash caching, they have primary level of the flash cache tiering. And for the actual capacity tier, there will be 2 options. Either will be shipping the SPDK and NVMe as a Fabrics running, let's call it storage bricks as the capacity nodes. So they won't do any tiering, they won't do any communication, these lower-end nodes between themselves. They will be acting, their job will be pretty simple, just to take a bunch of the NVMe cards and expose them over the NVMe as a Fabrics protocol and let StarWind control nodes build a huge unified and fast namespace from them. So adding, as long as the central controller nodes are not running out of the CPU horsepower, and with RDMA protocols, it will be pretty difficult to do. The whole raw capacity will be added with Backend NVMe or the Fabric capacity bricks. And this is scenario number 1. And scenario number 2 will be having as a backend storage somebody like doing massive parallel file systems or massive block storage, let's say, for example, Ceph. Ceph is a great piece of the software. It scales petabytes, it does erasure coding, and it has very high levels of fault tolerance, automatic rebalancing. I mean, just great. It has one little issue. You need many nodes to get aggregated, reasonable, good capacity. Performance from the capacity. So with a typical Ceph system, it runs out of IOPS long before it runs out of the capacity, which isn't good. And it's ridiculously slow for writes. So what we'll do, we'll fix it. We'll inject ourselves, we'll talk, at StarWind backend, we'll talk direct what's called Redis protocol to Ceph, and we'll use Ceph just as a huge backend storage. Doing huge acceleration to it, because all the writes will initially come to our controller nodes, where they will be kept for a while, up to a point when the onboard flash is filled and we have to offload it. And also we'll provide the management level to Ceph and all the certification stuff, because VMware and Hyper-V, they will be talking to StarWind nodes, so they will, instead of talking slow Linux iSCSI implemented at Ceph, they will be talking, let's say, for example, Hyper-V, they will be talking SMB direct to StarWind, and also the management integration of the StarWind is much better than these guys at the back end. So this is where we're going, because we are getting more and more requests from our customers that they like our solution, but they are getting to a point where from the capacity point of view, we don't fit really well. So we have to say goodbye to the customer, and they're going buying somebody else. It's much better to retain the customers than to make a new one. That's why we see calculate the amount of the requests we're getting and see the life cycle of our customers, and eventually.
So you call this like a storage virtualization solution kind of thing? I mean,
yes.
Where you're virtualizing the underlying backend storage?
Yes. So it will be, it will be, this front end will be the same. So Azure will be shipping the whole solution. So if customer is like going for 100% hardware installation, there will be controller nodes done by us. And there will be capacity nodes also done by us, sold by us, with the firmware and everything talking in Vimeo as a fabric. Or if the customer, let's say, has existing, for example, Ceph storage system, and he wants, run virtual machines out of it, and he doesn't want to cry when he does it. So he can go and inject us in the middle. This is absolutely not new approach. It's IBM XIV, and also it's the company.
More SVC than XIV.
Yes, exactly.
So
and also data core and a whole bunch of guys.
You could potentially have like NVMF, Ceph, and Lustre all operating concurrently underneath one, metadata control node set. And you can migrate the data between the two or something like that?
Exactly. So it won't be just, they will hold the initial level. This is when I was talking about the tiering and told that we are slowly and steadily moving from just doing what's closer to caching to closer what's tiering. Because with this configuration, and it's pretty easy, we're getting to a point when if we're talking about 3 2U boxes, you can pack quite a lot of the raw flash inside of it. I'm not even talking about open SSDs right now, where the all flash is raw, but I mean just commodity NVMe cards. So quite a lot of like 10, 15, 20% of actual capacity can still be at this point run at the controller nodes.
Okay. And we blame the guy who made the slide for the controller node not being HA?
It's actually, if you'll see, there are 3 of them. It looks good on the PC, but not very good on the
We'll blame the projector.
Yeah, it's just a projector.
But they are HA.
Yeah, they are. There are 3. There will be, is it 2 or 3 of them?
They're running the same code as your storage appliance.
Yes, exactly.
Right?
Yes.
So it's just using a different backend storage instead of the stuff.
Exactly. It's a little bit different configuration from the hardware point of view. Mm-hmm. So obviously it's a different protocol for the backend.
So it's still Windows running on that box, though.
We are moving on these. So we initially will be running a mix of the Windows and Linux. So the backend storage will be always Linux. And I've told so for the capacity nodes, there's no way, to run Windows on that.
Yeah, no, the only, I can hear objections from my clients on the, that are going to be running Ceph or they're running Cluster. They're usually trying not to run Windows in their environment.
Exactly, but as long as you're buying the box, this is something I'm like telling to you, and most of the customers, you most probably don't know what operating system your Tesla runs inside. You shouldn't be, you don't really need to know. Well, some guys, like crazy guys like me, they do reprogram their cars themselves, but not many people do that. The same over here. As long as the customer doesn't need to know what operating system powers his storage appliances, he shouldn't care. But I absolutely hear you and absolutely right, and a lot of people don't buy anything which is based on Windows, and you can't do anything with that. It's just like haters gonna hate. But for us, it's not political, it's just technical thing. We're getting to a point when to do some things with Windows, we need to change too many things. We need to, to get deeper inside, the operating system, storage network stack, and to apply too many modes.
And so something like this also supports all of your protocols, so iSCSI, NFS, SMB.
Exactly. Thing, right?
Exactly.
And you're providing effectively a global namespace across all the backend storage?
This is absolutely correct. So we'll be hiding. We won't use on the individual NVMe as a fabrics nodes or individual Ceph nodes. We won't be exposing them as as a unit. With Ceph is different because they have to do erasure coding, so they will talk to each other. But with the our own providers, they will run as simple firmware as possible. So the job is pretty minimalistic. Take NVMe card and expose it, make it being consumable by somebody else outside over the data mover protocol. That's it. There will be no logic. So all the data namespace management will be done with the controller nodes.
On the SSD side of things, I think it probably applies to the HCI offering. Do you have any SSD efficiency technologies like inline dedupe compression? And
yes, we do, and we'll get to this one. We do, just because you asked the question, we do run 4K inline dedupe, and that's mostly usable with, at this point with the hybrid systems we're providing. With all flash, you have to do a lot of number crunching to run inline dedupe inline. That's why it doesn't play really well with the all flash backend in our case.
So do you do that on all?
We do not do it on the all flash right now. We do it on the hybrid.
But all the other vendors look at it completely oppositely, whereby all flash you want to reduce the actual raw flash storage requirement, which is where they employ those technologies. So
yes, but this is not because we don't want to do it. Just because we are not able to provide all the we're doing some performance claimants, like we are taking all your raw flash and we're exposing it. You're not losing anything. We can do it with with just let's call it redirection. But if we are adding inline dedupe on top of that, if we're adding like all the snapshots and log structure and so on, we are losing quite a lot of the performance, so we cannot stay with this claimant anymore. Yes, we are just burning CPU. We need to go some different road.
What about compression?
At this point, we do not do compression, but it's part of the log structure file system. We're working on the compression, and we'll get to to this point.
Like next slide.
Yeah, next slide.
One more question on that slide. Do you assign policies to the backend storage? So how do you move volumes or data between the Ceph and the Lustre?
There's no really Ceph and Lustre at the same time. It's just one of those.
Okay.
So there's we apply management, and we assume somebody already has the system up and running. Mm-hmm. So our job is just to take the big data object and make it visible as with the interface which is acceptable by operating system at the top.
Okay.
That's it. Now we're getting to elimination of the I/O blender effect, log structure and inline deduplication. We had to do that because we were not very happy with the deduplication we are getting with Windows operating system, and because with spinning disk and with parity RAID, the write hole just kills all the performance. So this is how log structured file system works in our case. Again, I'm pretty sure that you are familiar with this technology, but this is for somebody who will be watching this video. The operating system maintains write queues, and within these write queues, they get some amount of separate memory regions should be stored on the disk, and they all get different spaces on the disk where they have to go. They're called logical block address, and they all get at this point they all get scrambled because typical multitasking operating system, especially if it's a hypervisor, they deals with many storage consumers inside it. So many writers, many readers. So the all logical blocks will be scrambled, and it's not like they serialize it or whatever. There are some techniques to optimize that thing, but they are not. They have limited scope of view. Let's call it this way. You can't do any kind of the elevator sorting inside anything which is quite deep, because if you want to write the very long I/O queue, you'll be losing the momentum and have a very high latency. So you don't want to do that. So initially, this writes comes to the deduplication layer. We chop all the requests into 4K blocks, and we run a hashing over them. And we are using I think we're using the some of the newer, not really well-known algorithm for this one. And at this point, we're using one of the proprietary techniques not to have all the long hash sums stored in memory, because if you'll try to do that, your deduplication software will become a memory pig, like ZFS, for example. That's why if ZFS, for example, I mean, I'm not trying to mock anybody, I'm just telling that I'm pretty sure that if original team of the ZFS would be in place and would be still working as a solution, then it will be a very good one. But at this point,
Yeah, but they all went off to DSSD.
What's that?
They all went off to DSSD.
Where are that?
And if they were developing it today, they'd have a third tier, and that tier would be just for metadata.
Okay. If ZFS, for example, needs a little bit more than 200 bytes to store a record for a block, then StarWind uses something between 8 and 12. Still, if you're running multi-petabytes backend storage, you still have to offload some of these guys on NVMe, and doesn't, make the performance real great compared to, again, to statements we've been making before. But for moderately small, I'm talking about terabytes of memory, still having everything pinpointed to RAM is okay. It's not okay if you're trying to run hyperconverged, because you need this memory for your virtual machines, but storage is okay. Then we get to a point which is called a page assembly stage, where we take all these separate writes and we put them and we get them into one big block, which is like 4 megabytes or so. And then we apply compression, which is not applied yet because we still don't have released one. This is an answer to the question, do we have it or not? Then we just write it as a disk. Big page, it touches all the, all the disk in a strip. That's why dealing with many disks in a parity RAID is okay. There is just one sequential write of many megabytes, and that's pretty much it. And then all writes go like they're getting with a tape. So there is no, there is no data replace, there is no data overwritten, there is no, trying to write as a different addresses and so on. It just we treat the parity RAID just like a big tape.
So you have some sort of a requirement for NVRAM or something like that to support HA, things of that nature, or?
These ones, we can do it with as long as you run a UPS on both all three controller nodes. We can do without the flashing.
Yeah, they don't acknowledge
we skip it at this point. We skip it the stage where the data is getting written from dynamic memory to flash, but it's just for simplicity.
And what's the size of the dedupe block?
Dedupe block,
Yeah.
4K.
Okay.
So it's native block of the device.
So if you're getting a large write coming in from the protocol level, you're splitting it up into 4Ks?
Yes. Yes.
Sounds familiar.
Just for the duplication to be applied.
And in one page, you can have multiple LUN blocks?
Yes. Yes.
Not just the same LUN would be in one.
No, it will be completely scrambled. So the backend, if at this point we have multiple LUNs, which is a case for any installation that does vVols, obviously there will be different writes from different LUNs. So the backend storage is not, it's not something.
And the snapshot granularity is at the LUN level, vVol level?
Here we're getting to a point, so these are technical snapshots. If we need to have a consistency inside the namespace, which is LUN, then there's a snapshot mechanism applied at a different place. These are, let's assume for simplicity, then we're just dealing with a single LUN, because it will make things simple. If it will be a single LUN, we'll get a bunch of the technical snapshots. We write in the consistency points. Let's say the power goes off, and one of the big benefits we have, except eliminating random writes, we don't need to scan anything, because what we need, we just need to check the tail of this log and discard some non-atomic writes. So we are going to lose, like, I don't know, maximum 4 megabytes of the data. Then we are getting one of these technical snapshots at some point being, like, let's say, kept in sync with if operating system on the top of us, if somebody is smart, like for example, Microsoft Windows has a volume snapshot services. We'll be able to synchronize Windows, keep in sync Windows snapshots with some of our technical snapshots, and this will allow the instant recovery and very efficient snapshot implementation.
Two questions.
Yes.
Number one, how often do you cut these, what you call technical snapshots? They're really CPs, right? They're consistency points. How often? What's the driver that makes that happen?
It's not the driver. It's just, you know,
Not physical
it's part
driver.
of our implementation.
What's a motivator?
And it's completely user controllable. So you can make it so we want one of the technical snapshots become, let's call it a real snapshot. Let's every single minute we can do that.
Yeah, I mean, because like for instance, NetApp does every 10 seconds, or when they have their.
It's completely. I mean, it's controllable, but you know, if we want, you know, to make this data consistent, we also have to do some, you know, job at the level up.
Yeah.
And
BSS and stuff
yes,
like that, yeah.
exactly. So that's why you don't want really to do this kind too often.
Yeah, right. Now, what about you have the dedupe layer, right, and the metadata. Do you replicate that metadata across other nodes, or is this deduplication node specific?
Yeah, we do not deduplicate metadata at this point, and the reality is, if we want to do that, it will be very, very inefficient.
Well, not deduplicate the metadata, I'm saying, but the metadata for the deduplication of the data.
We do not. We do not. We replicate, let's say, some fixed state. So we run an infinite state machine to control this one. At some points, we just, you know, to replicate, instead of replicating the data, we are replicating the state of this finite state machine. Mm-hmm. So on the other node, the code will be interpreting these states and generating some out of data. So from the customer point of view, from the consumer point of view, all the different, you know, siblings will be the same, but inside they won't be the same. So we'll maintain data coherency and data consistency. That's it. But for our internal metadata can be different for, you know, for.
But if I fail over and I have a deduped one that's replicated, I have access to that metadata.
It will work on the level of the technical snapshots.
Okay. It's on the disk.
A snapshot is a snapshot of your whole system. It's not just a snapshot of a LUN or something like that. Is that?
Yes.
It's the
so
whole.
it's a consistency point of the storage.
Yes, it can be done this way. I mean, it's a very interesting tech, and to be honest, we're finding some very, you know, somebody's coming and telling like why don't you do this and why don't you do that? And we say, well, you know, we never thought we could do that, and we can do it. It's like Lego bricks, which is that's the reason why I'm doing IT thing.
And you maintain data and cache coherency by maintaining state synchronization across the nodes?
For some things, these are raw data. For some things, for LSFS, it's maintained the same state by replicating finite state machine states. So again, if you compare the disk layout for two systems that are part of the HA, they won't be the same.
Yeah.
This is how caching works with what we do. So number one, it goes to RAM cache, where the data getting written by operating system, where we take writes from somebody who's talking the same block protocol we can do, because we are block inside. So we run iSCSI or ISOR inside, or in VMware the Fabrics soon, and all the file protocols are put on top of the shared block LAN. That's why we talk blocks. Then data goes from RAM. It usually gets into flash cache, or it's written to the tail of the log. And at this point, you see that there are snapshots, and the blocks are organized there. Because log structuring is a great technique, except it brings one huge drawback. So you do not have any more, you have very predictable writes, and you have great performance for writes, but you get, let's say, unpredictable performance for reads, and the worst thing is the performance is, is a function of how sequential the data was actually written, because it gets scrambled when it's written. And one of the things we are doing, sometimes we still need, if all the content getting deleted, we can't do in place, we can't do in place data writes. That's why we read all snapshot, change the data, and write it as a new one. So taking things from the tail of the log and put it on the head of the log.
So the garbage collection is done,
exactly. Is
that constantly rather than on a?
No, it's not constantly running because it will be still in IOPS from the system. So we're doing it just on the demand. I mean, when we really need it. And one of the things that the garbage collector is also doing, it's doing a serialization inside the snapshot. So we are trying to still, if you have a bunch of the randomly written blocks, we do elevator sorting inside the snapshot. So it will be better if somebody is trying to do the sequential read, he'll get, let's say, more reasonable, more predictable performance. Still, there is a flash cache for reads over here, and that's one of the reasons why, for example, if we'll take Nimble, they called cache accelerated sequential layout. Because you still have, if you're using this approach, you still need to have as small amount of reads as possible, and it makes huge and very efficient flash cache pretty crucial to this configuration. So we have a ratio of maybe like 10% of the flash being flash memory being assigned to become as a cache. So if we have 10 terabytes of backend storage, we do recommend to have at least 1 terabyte of flash to get, to decrease amount of possible reads actually touching slow block structured backend storage.